Hey guys, so I got a video coming at you about our kind of part 2 of covalent bonding with VSEPR geometries and hybridization. Alright, we are going to use a theory called valence shell electron pair repulsion, or VSEPR for short, to predict the shape that atoms will make or molecules will make. So that's the whole idea. If you hear me say molecular geometry or VSEPR geometry, I'm talking about the way the atoms are arranged around a central atom. What we need to know is that lone pairs, so these are electron pairs on that central atom, or whatever atom we're focusing on, those lone pairs take up more space than another bonded atom. The reason is lone pairs are only on that atom. So let's say I have an atom, A bonded to B, but A has lone pair. This lone pair takes up more room on A than atom B does, because this lone pair only belongs to A, whereas these electrons in the bond right here belong to A and B. Okay, so we also need to think about if there are multiple lone pairs on an atom, like this guy, those lonely pairs are going to repel the lonely pairs from, these lonely pairs are going to repel these guys. So knowing that lonely pairs avoid each other and that bonded atoms and lonely pairs want as much room as possible, we are going to make basically the biggest angle possible between lone pairs and bonded atoms. Alright, so how do we figure out the VSEPR geometry? Well, your first step is you have to draw the Lewis structure. You cannot tell the VSEPR geometry just by looking at the chemical formula. So you draw the Lewis structure, and then you can determine what family or what base shape the structure comes from. And so basically how many bonded atoms, how many lone pairs, that will tell you the base shape. And then you can determine the molecular shape based off the shape of the molecule will make just by looking at the bonded atoms. We know the lone pairs take up the most room, but we describe the shape based off of those bonded atoms. Alright, these are the base shapes, or the family that I was talking about on the last slide. Really what makes these the base shapes is that they have no lone pairs. So these shapes don't have any lone pairs on the central atom. They might have lone pairs on these green kind of edge atoms, but not on the central atom that we're focusing on. So our first base shape is linear. We have a central atom here, and there are two bonded atoms directly, and the angle is 180 degrees. Why is it 180 degrees? Well, these two green atoms want as much room as possible, and the way to maximize that is putting them 180 degrees apart. The next base shape is our central atom, and it has three bonded atoms directly to it, and these guys are spaced at 120 degree angles apart. Why 120 degrees? Well, that's the maximum space. If you take a circle 360 degrees and divide that by 3 sections, you'll get 120 degrees. Tetrahedral is our next base shape, one central atom with 4 bonded atoms. It makes a tetrahedron, and these guys are 109.5 degrees apart. So in 3D, you got these almost like a triangle base here, and then you have your kind of pyramid top piece. That's where the tetrahedron name comes from. Okay, then we have our central atom with 5 bonded atoms. This guy's called trigonal bipyramid, and we have 2 angles. Okay, really what's happening, if you connect these guys, I call it the belly or the stomach sticking out. Okay, we have a triangle. Okay, these guys, just like our trigonal planar, are 120 degrees apart from each other, but I can go up here. Sorry, I'm trying to make this 3D, but here is one pyramid, right? And so from this green atom down to this one, that's going to be our 90 degree angle. Okay, so there's our trigonal 1 pyramid, but if you notice, we can also go down to this bottom piece, I call it the feet, and make a second pyramid. So we have this kind of 2 pyramids, one right side up, one upside down. That's where we get the bipyramid, 2 pyramids. And last but not least, we have our central atom bonded to 6 other atoms. All of these are 90 degrees apart. It's called octahedral. If I ran the world, I would call this guy square bipyramid, because it's just like trigonal bipyramid, but instead of the base of the 2 pyramids being a triangle, it's a square. So there's my belly is a square on this one, and we can go up here. There's our top pyramid, and you can do the same. Here's the upside down pyramid on the bottom. Okay, octahedral, I would call it square bipyramid if I ran the world, but I don't. Okay, so let's say that you decide that the steric number, or the number of things attached to the central atom, is 4. Okay, so we're in the tetrahedral family because there are 4 things bonded to the central atom. Okay, so let's say we replace one of those items, not with a bonded atom, but with a lone pair. So that's this yellow guy here. So now our central atom, something like this, has a lone pair, and it's bonded to 3 different atoms. Okay, the shape of this is described based off the actual bonded atom. So this one is called trigonal pyramid. We ignore what the lone pair is doing, even though it's there, when we describe the shape. So it's just a triangle-based pyramid, trigonal pyramid. Okay, if we replace 2 of those atoms with 2 lone pairs, like water, we get something that looks like this, okay, and this is a bent shape. Why is it called bent? Well, it looks linear to me, but someone bent it over their knee. They snapped it in half. We get that bent shape, okay, and we're not really going to focus on this. It's another linear one, but I wouldn't base it off the tetrahedral one. Okay, what you notice here is that we started with an angle of 109.5. When we add a lone pair, this lone pair, remember, lone pairs take up more room. Okay, so this guy's really big, taking up a lot of space. So now the angle is 107.5. Okay, a lot of times the AP exam will accept this less than 109.5 because we know that lone pair's squishing it down. Okay, and then this guy, we got 2 big fat lone pairs. Picture 2 big balloons kind of pushing everything down, 104 degrees, or AP exam accepts less than 109.5 degrees. So a lot smaller than 109.5. All right, if you have 5 things attached to the central atom, we are in the trigonal bipyramid family. So here's again our trigonal bipyramid. We got our 90 degrees, our 120 degrees. Okay, notice what's happening here. If I replace one of the atoms with a lone pair, they actually took this molecule, I'll mark this one green and green. They actually took that and flipped it sideways. Okay, and we are replacing one of these atoms, I'll do yellow. We're replacing one of these atoms in the 120 degrees in what I call the belly with the lone pair. So let's talk about this. Why are we putting the lone pair there as opposed to where the green top and bottom, right, head or feet? Why are we putting the lone pair on the belly? Well, if you look, the belly, all of these atoms have 120 degrees of wiggle room, whereas these top and bottom only have 90 degrees between it and the closest atom. Okay, so a lone pair, remember, takes up way more room than the bonded atoms, big fat lone pair. So we would rather put that lone pair on the belly or the 120 degree mark because that will give it the most possible space. Okay, we still have 90 degree and 120 degree separation, and this guy is actually called seesaw. Here's why. If you picture the shape, here's my central atom, here's a bonded atom, here's a bonded atom, and then I have kind of one leg coming out towards me. I'm going to use the wedge drawing to show that it's coming towards me, and a dashed line. This is going back into my tablet screen. Okay, again, when we describe the shape, we don't describe the lone pair, even though I know there's one lone pair right there. Okay, but what I want you to picture is I want you to picture a small child sitting here like this, okay, and a small child sitting here. If they were at the park, do you see how this guy could go down, this guy could go up, and then it could go down, and then it could go up, just like a seesaw, right? That's where this gets the name. It's a seesaw. So picture kids playing at the park. Okay, if we replace 2 of those atoms, so now I'm going to replace one here, okay, replace 2 of those guys, here's my green head and feet, we get what's called T-shaped. So we have our central atom, we have one in the plane of the smartboard, in the plane, we see the letter T. Okay, and lastly, if I replace that third bonded atom with a lone pair and I flip this guy sideways, there's the head, there's the feet, okay, we get just the linear shape. So we're left with central atom, linear shape, 180 degrees. All right, now we have our octahedral family. So if there are 6 things on that atom, that central atom, so again, we got 90 degrees everywhere for our octahedral. What's interesting here is since they're all 90 degrees, the top and the bottom actually feel like they have a little more room, less tightly packed, even though they're all 90 degrees apart. So we're actually going to replace top and bottom with lone pairs. So if I replace one of the atoms with a big lone pair, so there's my lone pair of electrons. If we describe the shape, remember we don't use the lone pair. This guy connects, still my square, but we only have one pyramid this time. So this guy with one lone pair is called square pyramid. And last but not least, if I replace the top here with the lone pair, so we got big lone pair on top, big lone pair on bottom, taking up a lot of room. The last one is called square planar because it's on one plane, just a flat square shape. All right, here's our first example. Describe the molecular structure, so that's talking to me about VSEPR, of a water molecule. So we know water is H2O. Okay, O is our central atom. So just a little review. I know we did this in class, but oxygen has 6 valence electrons, and each hydrogen has 1 valence electron. So overall, this guy has 8 valence electrons for us to work with. We can't have more or less than that. So this is going to be a covalent bond, so I see these two could share and form a bond. These guys could share and form a bond. So I'm going to redraw, and I'm actually just going to change the shape so we can see it a little bit better. You do not have to change the shape on AP, like the way you draw it. You don't have to do what I'm doing. You can just simply mimic, turn those circled ones into the bonds, and leave any uncircled lone pairs like this. You could leave it, but I find that this helps kids see the shape. Okay, so what I see is there are 4 things bonded to the central atom. We got 1, 2, 3, 4. So this is from the tetrahedral family. But if you replace 2 of those bonded atoms in a tetrahedral with lone pairs, we get a bent shape. Okay, that's why I drew it this way. If you drew it linear, kind of like how I set it up originally, that's fine, but you need to call it bent. Okay, well, we know that a tetrahedral is 109.5, so if I add 2 lone pairs, that's less than 109.5 degrees, or more specifically, 104 degrees. Either of those answers are acceptable. All right, so when phosphorus reacts with excess chlorine, the compound phosphorus pentachloride, penta is 5, PCl5 is formed. In the gaseous and liquid states, the substance consists of PCl5 molecules, but in the solid state, we have a 1-to-1 mixture of PCl4 plus and PCl6 minus ions. So they want us to do our geometric or our VSEPR structures for all 3 of those. Okay, so let's start with PCl5. Whoops. We're rolling. Okay, PCl5 has 40 total electrons. Okay, so I'm just going to sketch this guy real quick. Oops. Okay, there's my PCl5. Okay, if we look on our central atom, there is 5 bonded atoms and no lone pairs. So that gives me a trigonal bipyramid shape. And we know that these angles are 120 degrees. Say hi to Phoebe, everybody. And this angle from the top to the belly is 90 degrees. Okay, let's try the next one. We have PCl4 plus. This guy is going to give me 32 electrons. So I got my P. Don't forget my brackets. It's a plus charge. All right, hope you can double check, but hopefully that's my 32 electrons. Didn't miss any, I don't think. Okay, I look at my P. I see that there's 4 things bonded to it, no lonely pairs, so that's a tetrahedral shape. And all of my bond angles are 109.5 degrees when we're tetrahedral. All right, I slid on over. Now we have PCl6 minus. That guy's got 48 electrons. chlorines. I always, every year, have kids say, Miss Butler, do we have to draw all those lone pairs on the non-central atoms? Why, yes, great question, you do. And if you want to complain about it, I feel like, wow, look at how great your life is right now that you're complaining about putting dots on things. Remember when we were learning acids and bases and titration curves, right? There's harder things for you to complain about. Okay, don't forget your brackets. -1 charge. Okay, so on this guy, I got 6 things bonded to the central atom. That gives me an octahedral shape, no lone pairs. And we know that these angles and these angles are all 90 degrees. So all 90-degree angles on that guy. Okay, now that we're done with VSEPR, we're going to talk about this idea called hybridization. Okay, so here's a methane molecule. Methane is CH4. And we know some things about methane, okay? We know that methane is tetrahedral, and all of the angles between those hydrogen atoms is 109.5 degrees, okay? I also know that all of these carbon to hydrogen bonds, these guys here, all of them have a distance of 108.7 picometers. All of them are the same distance. They are equal. Okay, if we look at the electron configurations, carbon is 1s2, 2s2, 2p2, and hydrogen is 1s1. Well, this is where the valence electrons are, and we know the valence electrons are the ones that bond. Well, to do this, for carbon to form 4 bonds, to share 4 electrons, it would be using the 2 electrons in the 2s orbital and the 2 electrons in the 2p orbital. Okay, well, here's what these look like. Here's your 2s orbital, it's a round shape, and your 2p orbital, remember when we draw our p, when we do our energy diagrams, there are 3 orbitals. Okay, we have one on the x-plane, one on the y-plane, one on the z-plane. So what I'm seeing here is carbon has 2 different types of orbitals that it's going to be bonding with. Okay, and all of these from carbon are going to try to bond with the 1s orbital, which is more simple, just a round sphere from hydrogen. But how, in my trying to riddle me this, how are 2 different types of carbon orbitals going to bond to form these all the same angles and all the equal bond length when we clearly have 2 different shaped orbitals? And in addition, if you look at how those p's form, if you put them all on one graph, they are clearly going to be at 90-degree angles from each other, right? That's going to be a 90-degree angle. So, like, how are we getting this magic 109.5? I'm confused how this is going to work. So, what comes of this idea is that the localized electron theory, what we've been using when we think about our electron configurations, it's not incorrect, but it's not perfect for bonding. Carbon has to have a different set of orbitals than this 2s and 2p combo that it uses for bonding. Okay, the 2s and 2p is not what's used when we see the bond between the carbon and the 4 hydrogens. So we get this new theory called the valence bond theory, okay, and so we're kind of extending what we know so far to figure out how these bonds work. So this idea involves hybrid orbitals. So basically we are mushing or blending those atomic orbitals, okay, that for carbon's case, we're talking about the 2s and the 2p. We are blending those to create kind of a in-between energy orbital that's equal, that is all the same, because 2s and 2p are not equal in energy. Okay, so let's look at methane, which is CH4. Okay, we know that CH4 has equal length bonds, and they're all 109.5 degrees apart, whereas that we looked at the p orbitals, those would be 90 degrees apart. But once it begins to bond with hydrogen, so we take this carbon, we put it in the presence of hydrogen, it starts to bond, okay, we get a hybridization to occur of the 2s and 2p orbitals in carbon, which changes the way they look. They are no longer the sphere and the separate dumbbells. Okay, we are not getting that anymore. Okay, we get a new shape, and notice they are all equal in shape. So we are bonding all of these together. So here's exactly what I just drew, which was a waste of time. I'm sorry. Here's my 2s. Here's those p's. Okay, we are blending them. Notice all of these kind of look like mushroomy shapes. They are all identical. And what happens then if you can kind of picture them smushed together here, okay, so here's carbon's atomic orbitals. If you smush them all together in the center, the orange lines up, you can put the 1s from one of the hydrogens, 1s, 1s, and 1s, and that's how we get the 109.5, and we get all of these bond lengths to be equal, okay? What's interesting is now we have these 4 identical bonds, but look at the energy. So here's carbon separate, just the orbitals of carbon separated, 2s2, 2p2. When we get this new hybridized orbital, we give it a new name, we call it sp3, okay? And notice that this is lower in energy than the 2p orbital, okay? So we kind of bring down the energy here, this one rises up a little, so we get this intermediate all equal. All right, ammonia, NH3, which I can draw a quick Lewis structure, also uses hybridized orbitals to bond. It has a lone pair, so you can do hybridized orbitals even if there's lonely pairs. So just think of these electron pairs as sites where electron density can either be like lonely pairs or bonded. So when we look at like the naming of the hybridized orbital, you look at how many things there are, almost like when we figured out what family it was in. This is part of the Tetrahedral Family, even though it's called trigonal pyramid. Anything with 4 attachments, whether they are bonded atoms or lonely pairs, are going to be sp3 hybridized. Okay, it is possible, like we talked about in class, to have multiple bonds, so double bonds and triple bonds, but that lowers the number of hybridizing orbitals, so we call multiple bonds pi bonds. So the pi bonds come from this sideways overlap of p orbitals. So if here's a p orbital here, here's a p orbital here, okay, and what happens then is we can actually hold an electron above and below the axes, but notice in the middle here in this green, this is a sigma bond, okay, so you can't have pi bonding without a sigma bond first. Basically, you can't have a double bond without a single bond first, right? You need to have that one bond. So this is going to happen when we have sp or sp2 hybridization on the central atom. You won't have it with sp3 because that's all single bonds only, not double or triple bonds. Carbon, a lot of times, will do this with nitrogen, oxygen, phosphorus, and sulfur because they have p orbitals available. So here's the real summary that we need. If I ask you for hybridization, we are looking for how many bonded atoms or lonely pairs. So add those together. If there are 2, your base shape is linear and it's sp hybridized orbitals. Okay, if you have 3 things on that central atom, your base shape is trigonal planar, but it could also be bent. Okay, it could be a lone pair as well. That's going to be sp2. Okay, 4 things on the central atom, that's going to be our tetrahedral. So we're looking for tetrahedral, we're looking for trigonal pyramid, we're looking for bent. That's sp3 hybridized orbitals. Anything with 5 bonds or bonds and lone pairs, that combo is in the trigonal bipyramid family. It's dsp3 hybridized. And lastly, anything in the octahedral family, so 6 things on the central atom, lonely pairs or bonded atoms, that's D2sp3 hybridized. Okay, we are almost done. Sorry, this is a little long. I've been having fun with my Apple Pencil. But this kind of puts it all together. So describe the bonding and hybridization for ammonia, which is NH3. So we have NH3. That has 8 valence electrons that we can use in our picture. So we have our nitrogens, got 5, 3 hydrogens, each have 1. Sharing is caring. Maybe I'll try. Nope, just kidding. Go with color. Right there, right there, right there. So I'm going to redraw those circles as bonds. Come stand out. We got lonely pair. So what I see is we have a tetrahedral base shape because 1, 2, 3, 4 things, but one of those things is a lone pair. So that changes the geometry to trigonal pyramid. Simple kind of triangular pyramid, which means we are less than 109.5 because that lone pair takes up a little more room than it did in the tetrahedral shape. Okay, but there are 4 things attached to that central atom. 1, 2, 3, and the lone pair counts, which means we are sp3 hybridized. All right, same idea. We have N2. It's got 10 electrons for us to work with. This one's a fun one. They can share. Okay, if I stop here, this nitrogen has 2, 4. The bond makes 6. This guy has 2, 4. The bond makes 6. Unhappy. Okay, so we need to use multiple bonds when the atoms are unhappy. Okay, so if we do a double bond, 2, 4, 6, 7, still unhappy on both sides. So let's do a triple bond. So I'm going to redraw this so it looks a little nicer. We have a triple bond. Okay, and so there's our molecule. What we see here is we have a linear shape, which means we are 180 degrees. And all we have is that we have 2 things, kind of one bond, if we focus on this end. We have 1 bonded atom and 1 lone pair, which makes us sp hybridized. Okay, so this lone pair and this bond, even though it's a triple bond, that does not make a difference. All right, last one. I want you to pause the video, try this for yourself. This is a true test if you understand VSEPR and the hybridization. All right, check your answer, and that is where we will stop today. We're going to do tons of practice in class and maybe give you some time on your problem set.